Okay, E12, welcome to your video tutorial today. Today we're going to look at the role of machine code in the execution of a program. More particularly, we are going to be looking at the CPU and how it works. So if you want to know where we are in the syllabus, 9.2.3, the role of machine code in the execution of a program. We're going to look at how the CPU handles a machine code instruction, basically, any code that it's trying to, how it's formatted, what these random things are that are called registers, what this fetch execute cycle is, what a program counter is, what an instruction register is, and these linking and things called DLLs. All of which seems pretty foreign to you right now, but hopefully by the end will make a lot of sense. So essentially what we're looking at today is how does the hardware in my computer, the brains of my computer, the central processing unit or the CPU, handle my code? How does it work? Okay. So what kind of questions can you get asked in the HSC? Well, I've just pulled the last couple of years. The 2018 HSC has a question, what happens during the fetch step of the fetch execute cycle? Not too sure what that is, but I know it's listed here, so it's probably going to be something that I have to look at. Again, we'll have a look at the fetch execute cycle. Distinguish between the program counter and the instruction register. Again, these are new terms to me, but I've noticed that that's actually what's quoted directly in the syllabus, so that's probably something really important to know as well. And then these scenario-based questions, which seem very foreign and very confusing, but hopefully they will make sense. The instruction set for a particular CPU is as follows. It wants to know, first off, what's a register, what's an accumulator, and then outline the fetch execute cycle as the first instruction above is executed is a C. Okay, so it has all this random stuff that I can't really read or make sense of yet. But then it wants me to outline the fetch execute cycle as it pertains to these two things, which hopefully will make sense. Prior to the executing a fragment of code, the contents of memory locations are as follows. What are the contents of memory locations after the execution? What is the role of the register in the execution of this code? Okay, so again, this word register pops up again. A weird scenario where I have to apply, and again here, but otherwise it's really asking me to pull a lot of content from this or this or this or this or this. Okay, so let's get started. So we are going to look at how the CPU executes machine code commands. Okay, two things that you need to understand. Well, what is machine code and how is machine code executed by the CPU? What we look at today will actually be built on next lesson when we look at how we actually can translate source code, either by compiling it or translating it. So a lot of today's work, you really need to pay attention because it's going to be actually built on in the next syllabus dot point. So machine code is the native language of the CPU. Okay, it's a collection of instructions that tell you what the CPU is going to do. Okay, each instruction is in binary or is a set of ones and zeros. Okay, so machine code is ones and zeros. We are going to look at next lesson how it gets from my source code to the ones and zeros. Today we're just simply looking, okay, once it is the ones and zeros, how does the CPU actually handle it? Okay. One machine language instruction will usually translate into several instructions. So the CPU contains a set of permanent instructions for how to do stuff, but one machine language instruction will usually translate into several little tiny instructions. Okay, and different CPUs will have different ways of handling machine code. Okay, machine code instruction is constructed into two different components. So when I look at these ones and zeros, there's two different components. There's something called the opcode, which is a short code which indicates what operation is to be performed. And the operand or operands is an indication to where the data is required for the operation is located. So where am I looking for this? And when we have a look at RAM, and how registers and things are saved, this will hopefully make sense. You know, what's going to happen? Where do I find, like, where's the data required to do this operation? So if I'm adding two things together, that's cool, but what two things and where are they? Okay. The other concept that you guys need to understand before we get into it is assembly language. So assembly language is a way of writing machine code so that it can be understood by humans. Now, when we look at these scenarios, this is assembly, okay? This is essentially assembly language because it's pretty much summarizing, like it's telling you exactly what the CPU is doing, but it's in a way that you can actually read it, like load, add, sub, mov, JMP, JLZ, HILT, halt. That is assembly language. And again, oh no, there's no more examples. But if you have a look through the other HSC papers or trials papers, you'll see lots of assembly code language when you're looking at the CPU and what we're looking at today. Okay, what actually happens is the assembler code instructions are converted into machine code and processed by the CPU. You will see assembly, though, in most of the scenarios that are asking you to decode machine code instructions, just so you're able to somehow read it. Okay, how is machine code executed by the central processing unit? Okay, this is the first concept, and you would have seen this earlier on in those HSC questions that we were looking at. It's called the fetch execute cycle. Now, in a moment, we're going to look in more detail at what the control unit is, what the arithmetic logic unit is, and what RAM is. Control unit, ALU, and RAM are the three hardware components that are involved in the fetch execute cycle. It's called a cycle because it doesn't necessarily start anywhere. I mean, if you were to pick a point to start for the first instruction, it would be fetching it from RAM, the control unit decoding the instruction and passing it on to the ALU executing the instruction and storing it in registers and in RAM. Sorry, in registers in RAM. Yeah, and then the next instruction is fetched by the control unit from RAM, decoded, executed by the ALU, and stored back again. This cycle goes around and around and around and around and around and around and around. So, in terms of the fetch component, this component here, fetch, the instruction at the memory address found in the program counter is read into the instruction register. Holy moly, what the hell does that mean? Okay, long story short, okay, there will be an instruction saved in RAM at some point in time that needs to be executed, okay, by the CPU. Okay, the instruction at the memory address, okay, there's a point in memory, in RAM, random access memory. There'll be a memory address saved here and it'll go, okay, it's that instruction's time, okay. I know that because the program counter will tell me that, and in a minute when we look at exactly what each of these things are, hopefully you'll be able to come back to this explanation and go, oh, okay, cool, I think I've got my head around that. Is read into the instruction register, the program counter is incremented to point to the next instruction. Okay, so it's a fancy way of saying the next instruction is picked up in RAM, fetched, and passed on to the control unit. Okay, the control unit, or that instruction that I've just fetched, is decoded into that thing that we were talking about before, an operand and an operator. Okay, what is the thing that I'm actually doing? You know, and where is the data that I'm actually executing? Okay, keep on going the wrong way, sorry. That's decoded into operand and operator. It's passed on to the ALU, and the ALU then executes the instruction. Okay, and the results are stored into the registers and also moved back into RAM. Okay, fetch, decode, execute, store. So, in order to be able to understand a lot of this subject-specific terminology that's going on here, like instruction register and program counter and what in the earth she's talking about, this ALU thing, you really need to understand the three major components of the CPU, which are the ALU, the control unit, and the registers. Okay, communication happens between these three parts RAM is actually separate. So RAM is a separate part. RAM is not actually part of the CPU. The CPU has three parts: the control unit, the arithmetic logic unit. So this and this are part of the CPU. And this other thing we keep on talking about, these registers, they're all part of the CPU. RAM is separate. Even though RAM is involved in the fetch execute cycle, it's a separate part of memory. Okay, so in order to really get what's happening there in the fetch execute cycle, you need to understand, well, what are actually the three components of the CPU. Okay, this ALU that actually executes the instruction can perform one of three functions: mathematical operations. Okay, so it can do addition and it can essentially do all of your mathematical operators: addition, subtraction, multiplication, and division. In our option topic, we're going to have a look and see, you're actually going to investigate and see how actually the only operation it can do is addition, and how to subtract or multiply or divide is actually a manipulation of addition. And that's super cool, but we're going to not be looking at that for a couple of weeks. It can also do relational comparisons, so it can work out less than, greater than, equal to, less than, greater than, or equal to, or it can do logical operators, and, or not, or. These things are also going to be explored in a bit more detail in our option topic, but they're the three functions it can do. It can compare things, relational comparisons, it can do mathematical operations, or it can do logical operations. Okay, the control unit. Think about this guy like the traffic lights. It coordinates the flow of data around the computer and within the CPU. It knows what data goes where and organizes it. So it says, okay, fetch, I'm going to take you. Yep, I'm going to decode you. Okay, you can now go over here and you can now be executed by the ALU. It's like the traffic lights. It's like the big Thomas the Tank Engine sitting in the middle, controlling everything that gets executed. Okay. Registers. Now, this word has come up a couple of times. Registers, there are several registers that are contained within the CPU, and their job is to store data before and after processing. So they're like a small little data storage. Okay. Some registers are permanent, some registers aren't permanent. Some of the time, some stuff will get saved in the register in the fetch execute cycle. It'll get saved in a register and also saved into RAM. Okay. These are the registers that are really important that you need to remember. The instruction register, and I remember seeing this in the fetch bit and the program counter. I remember seeing these in the fetch bit of the fetch execute cycle. The instruction register stores the current instruction being executed. The program counter stores the memory address of the next instruction. So the instruction register stores the current instruction. The program counter stores the address, the memory address, or the address in RAM of the next instruction. So if I go back, the instruction at the memory address found in the program counter is read into the instruction register. So the instruction in the point in RAM found in the register that stores whatever's next to be executed is read into the instruction register, which tells me the instruction that I'm actually executing. Okay, cool. I then say to the program counter, okay, I've got the thing that was next. You now look at, I've got the thing that you said was next. Now what's after that? That's what that's trying to say, guys. Okay. Another two that are really important that you need to remember is the accumulator, which stores the result of the execution by the ALU. So once the arithmetic logic unit actually executes an instruction, the accumulator stores the result. And then the stack pointer is another important one. It points to the most recently referenced location on the stack. Okay. The last concept, which isn't super important, and they are a little bit old, and they're only available on Windows, things called DLL files, or a dynamic link library. Okay. The intention behind DLL files was to improve the efficiency of executing instructions. Okay. Rather than putting lots of heavy pressure on the CPU to absolutely execute every single instruction, you instead had all these things called DLL files. DLL files contains a set of standard subprograms that perform system-like functions. So typical things that get executed. Typical things that get executed by my CPU. Okay. When I go to execute the program, the control is passed between, rather than going, so here's my source code, it gets turned into an object, rather than constantly compiling every single thing in my source code to get executed. Instead, what the CPU does is it goes back and looks for these common tasks and it just pulls it from this DLL file. Okay, they're only available on Windows. The idea was that, rather than executing every single instruction, I could just constantly point back to these DLL files and go, oh, here's the instruction that needs to be executed. Here's the instruction that needs to be executed. Here's the instruction. Rather than constantly having all of those hundreds and thousands of instructions sitting in RAM waiting to be executed, rather I just point to these DLL files and it executes it that way with a thing called a linker. To be really honest with you, nowadays it's not a super necessity because we have lots of RAM and way more efficient CPUs. But at the time at which they were made, 80s and 90s, it was really important because we didn't have as much. And that's it, guys. That's the content for that. So let's go back and have a look at some of these questions. Okay, things that you should be able to answer now. What is a register? What is an accumulator? Should be pretty straightforward, pretty easy. Okay, another question that should be pretty straightforward and pretty easy is these two. What's the difference between a program counter and an instruction register? Should be able to answer that. What happens during the fetch step of the fetch execute cycle? Okay, let's have a look. The program counter is incremented. A program is copied into the CPU for execution. Data needed to carry out an instruction in the CPU are moved from memory. An instruction is copied from memory and placed into the instruction register. Now, there is a lot of things in there that could be correct. This question is really annoying because it's all about little words. Okay, so let's look at this. The program counter is incremented. I know that definitely happens because if I go back to here, it says the program counter is incremented to point to the next instruction. I know that definitely happens in fetch. A program is copied into the CPU for execution. What? That doesn't even make sense. No program is copied. We're talking about instructions, so that guy's gone. Data needed to carry out an instruction in the CPU are moved from memory. Well, it's not really data that I'm moving. It's more the instruction that I'm grabbing, so C's gone. The only other one it could be is an instruction is copied from memory and placed into the instruction register. Now, I'm a little bit confused because program counter is incremented, but I did think something happened about the instruction register. Now, unfortunately, the answer's A, and I'll tell you why, but this is a really tricky one. The instruction isn't copied from memory and placed into the instruction register. It's read from memory, so it's taken from memory and put into the instruction register. It's not copied. So unfortunately, while D seems like a correct answer because both of those things happened, I know both of those things happen, it's actually read, not copied. So the correct answer is that the program counter is incremented. Okay, let's have a look at the 2018 trials. Okay, and let's look at the fetch execute cycle in relation to this instruction here and this instruction here. So let's have a look here. So if we're looking at the fetch execute cycle, I would do this having this guy and this slide alongside me as I went to write this. So the first instruction, this first add instruction is fetch from the RAM and read into the primary the instruction register. So this instruction in the fetch cycle is fetch from primary memory or fetch from RAM and read into the instruction register. The program counter is then incremented to the next address, so this sub-address, ready for the next execution. The control unit decodes this add reg 110 yeah, and adds the instruction into the instruction register, the operands are loaded from memory into registers. So like in this case, this is then decoded. It's decoded and then it's executed by the ALU, and the results are stored in the accumulator. So let me give that to you again. This instruction, this add reg1, 10, is fetched from RAM. And read into the instruction register. The program counter is incremented, to point to this instruction for the next time the cycle runs. The control unit then decodes this instruction into operand and operator. It then passes it to the ALU to decode it, to execute it, and that's then executed, and the result is stored in the accumulator, and then anything necessary is stored in RAM. It then goes to grab the next instruction. All I've done there, guys, is I've basically given my marker, I've basically given my marker this process, but just referred to these instructions. Okay, so with that, what I'd like you guys to do is to give this one a go. Okay, I think actually you might be missing a little bit from the top of that, so I'm just going to make sure that there's a scenario at the top of that, and give these two things, like give this question a bit of it, and obviously the answers for all of these, which are pretty straightforward, a go, and hopefully from that next lesson, when we look at translation and compilation, it'll make a lot more sense. Good job, guys.